Hello everyone. So today we'll start looking on chapter 16, Planar Kinematics of a Rigid Body. So all the chapters that we have taken before, starting from chapter 12, 13, 14 up to chapter 15, we were actually dealing with particles. We are studying the motion of the particles, and but in this chapter 16, we start dealing with the rigid body. And if you do remember that at the beginning of the course, we were discussing that we will study the motion of two types of body. It can be either particle or a rigid body. So it can be a particle or a rigid body. And the difference between the particle and the rigid body is the particle, it has mass, but there is no size, no shape for the particles. So during the questions in the previous chapters, we were not discussing anything, or we will not have any information about the size or the shape. We were not discussing we were actually only discussing the type of motions in terms of the velocity, position, velocity, and acceleration. And the size, the shape of the particle, there is no information about that. We don't actually consider that information. But now, starting from chapter 16, we start looking on the rigid body. So the rigid body will start have a size information, shape information that will be considered in the questions in this chapter. So we have a particle and we have a rigid body. In the particles, starting from chapter 12 up to chapter 15, we were discussing the position, velocity, and acceleration, and the position was per meter, velocity is meter per second, and the acceleration was meter per second square. Now the rigid body, starting for this chapter, will start having similar things like S was stand for the position, A was stand for the acceleration. Now we'll start using this new formula. Instead of the position, we'll start call it theta. Instead of the velocity, we'll start to call it omega. And instead of the acceleration A, we'll start to call it alpha. So theta is similar to the position, omega is similar to the velocity, and alpha is also similar to the acceleration. This is for the questions related to the particles. But for the questions related to the rigid body in this chapter, we start using this one if we are considered the size and the shape for the body. So theta is the angular and the unit is radius. Here is per meter. Omega, we start to call it not velocity, but we start to call it angular velocity. Alpha is the angular acceleration. So this is an acceleration for the particle. Alpha is the angular acceleration. Omega is the angular velocity. And here is the radius. Theta, omega, alpha instead of position, velocity, and acceleration. So in the particle questions of the particle, we were start giving the information of the velocity from the position by the int by the differentiation. So if you do remember, we have position, velocity, and acceleration. And if all of them are a function of time, if we are moving at this one, like if we need velocity information from the position, we will actually differentiate. But if we need to go back, we will integrate, right? Only if all the information here are a function of time. So the position, we have a position. The velocity is the derivative of the position. Acceleration is the derivative of the velocity. The same is here. We have theta, which is the angular, which is similar to position. Omega, or the angular velocity, is the derivative of the theta, and alpha, which is the angular acceleration, will be the derivative of omega. So we'll have theta, omega, and alpha. If we need to go like this one, we need to differentiate. If we need to go back, we integrate. integrate. So it is similar to this one, but we start to call it theta, omega, and alpha. Omega instead of velocity, we start to call it angular velocity. Instead of acceleration, we start to call it alpha, which is the angular acceleration. And in terms of the particles, when we have a constant acceleration, we had these three equations. The final velocity is equal to the initial velocity plus the constant acceleration times the time. The position of the final position is equal to the initial position plus the initial velocity times the time plus blah blah blah. And also we had the third equations related. We are using these three actually. We are using these three equations when we are dealing with a constant acceleration, like acceleration is 5, 3, 25 or whatever meter per second square. It's not when the acceleration is a function of time, like if we have something like uh, a is 5t squared plus 2, for example, is a function of time. So we don't actually, it's not constant actually. It's not constant. So this equation is only when we have a constant acceleration like 5, 3, 7 or whatever number. It's a constant number. But if it is a function of time, it means that the acceleration is changing over time. It's not the same acceleration at different time. So if we have the acceleration as a function of time, then we'll start to go with this one, the integration and the differentiation to get the other information. But if it is a constant, we start using this one. We are no longer using that one. That one, integration and differentiation, is only when it is all other function of time. The same here, if we have an angular velocity, we start to call it alpha, we'll start using similar equation. But since we are no longer using S, V, and A, we start to replace it with omega, theta, and alpha. So velocity is the same as the omega. We just the final omega will be equal to the initial omega, like the initial velocity here, plus the constant alpha, which is the constant angular acceleration, is similar to the constant here, time t. And the same goes for this one. We start replacing s with theta because s here is represented or similar to the theta. I will start to replace a or the acceleration with the angular acceleration of alpha. So we'll get these three equations similar to this one, but here we'll start to use theta, omega, and alpha. Theta is similar to the position, omega is similar to the velocity, we'll start to call it angular velocity. Theta is similar to the acceleration, and we'll start to call it angular acceleration. So the motion of the rigid body, because we are starting actually working on the rigid body that has size and we start consider the size and the shape of the rigid body. For the particle, we don't have any other type of motion. We only have translation motion. It means that there is a particle move from here and stop here, or if there is any particle here that we throw it up, it go all the way here, then it come back. So this is the initial position, this is the initial velocity. It come here, we study what is the position and what is the velocity at this position and what is the acceleration here, and here we will have another position, velocity, and acceleration. We don't actually consider the size and the shape of the particles. We haven't seen that the size and the shape, if there is a ball with a radius or whatever, so we don't actually consider that one. This is only for the particles in the previous chapters. But today we'll start on the rigid body. In the rigid body, we start actually consider the shape and the size of the rigid body. So the motion of the particle here is only one motion, and it's translation motion. We call it translation motion. It means the whole body here, it moved to this one, and there it moved here. But for the rigid body, when we are considering the shape and the size, we are actually having three types of motion. It can be either translation motion, rotation motion, or GPM motion. So starting with the translation motion. Translation motion is similar to this one. To be more clear, like if we have any rigid body and the translation motion, that this rigid body move all the way here. That's all. And if there is any rigid body contains of infinity points. So it means that at any point here, if there is any point here located on the rigid body, all the points will move the same direction with the same velocity, same acceleration, and they will end up here. So the whole body move from this position to this position with the same velocity, same acceleration, same position at any point. So if there is points, so there is infinity points that's located on this body. At any point here, they all are moving the same direction with the same direction with velocity and acceleration. So if we have a body here and it moves all the way and end up here, in terms of the straight line, or even in the curvilinear motion, there is a body here, move all the way here. This is also a translation motion. The second rotation, we have two types of rotation. Like if we have a fixed point here and we have a rod, and the rod is moving at this direction, for example. So what is the definition of the rotation motion? The rotation motion is when the body rotates on a fixed point that is located on the same body. So we are considering here, this is a rod, and the rod is connected with a pin fixed at this point, and it's rotating here. So it means that the body is rotating on a fixed point. So this body is rotating actually on this fixed point. So initially it was something, for example, like this one, and it will end up here, for example. So this one is rotating on at this fixed point, and this point is actually part of the body. It's not outside the body, but it is actually part of the body. So it moves from here to here, and it will end up here. So they are actually rotating. They are actually rotating on a fixed point, and this point is located on the same body. Another example of the rotation, if we have a disk, for example, and the disk is fixed with a pin point here, and the disk is moving at this direction, is rotating actually. So it is actually rotate on a fixed point. This is the fixed point, which is inside the body, or part of this body, and it's moving, rotating at this direction, or rotating on this fixed body. This is, we call it either disk, wheel, or gearbox. The third type of motion, we call it GPM. GPM is actually as a mixture of these two type of motion, translation and rotation at the same time. As an example of this type of motion is for example, a car. And there is a car here, and the car is moving all the way here, moved from this position, and it end up to this position. So this is translation motion. At the same time, we have a wheel here. The wheel is actually rotating, right? So they are actually rotating on a fixed point at the middle of this one. So it's also part of this body. So it's a mixture of translation motion and also rotation motion. So this is an example how the translation and rotation can be combined at the same rigid body. So we have an example of, this is a rigid body, a disk rigid body. This is a disk rigid body that is actually rotating at this direction. For example, they are fixing what type of motion? This is rotation motion. Why? Because based on the definition of the rotation motion, that the rigid body is rotating on a fixed point that is located on the same body. So the gear or the gearbox or the wheel or the disc is rotating actually on these fixed points, and this point is part of the body. So it is a rotation type of motion, and they are moving all the way here. So this type of motion for this disk, it must have theta information, it must have omega information and alpha information. Theta, angular velocity and angular acceleration. So this one, you should have these three information. Another thing that I want to mention, that at any point located on the disc or on the gearbox or on the wheel is moving from here to here. For example, if I have a point here, we call it A. If I have a point here, that is A. When this one is moving, then A start moving from this position to this position, then it will move to this position, etc. So at this point, point A, as a result of the rotation of the rigid body, will start moving from here, then it will move here, here, after some time will reach to this one. So this type of motion is actually translation motion. So at any point inside the rigid body or the rotation wheel or the gearbox or the disc, the point inside the whole disk is a translation. And translation, it must have position, velocity, and acceleration. But for the whole body, it must have theta, omega, and alpha. So at the same question, you will start having position, velocity, acceleration, theta, omega, alpha. So we have four types of information that can be located at the same disk or the same question. So we have this disk is rotating at this fixed point. The rotation of the disk, this is actually a rotation motion. So since it's a rotation motion and it is also a rigid body, so it have theta, it will have omega, and it will have alpha information. And if there is any point here, point A, that move as a result of the rotation, it start here at another time, after sometimes will come here, after another time will come here, etc. So the motion of these points is translation, and it should have position of A, it should have the velocity of A, and it will have also acceleration of A, and the whole body, it will have theta, omega, alpha. And this is actually the radius. So initially this is the radius of this disk, and as a result of the motion, how do we can get the final position of this one? How do we link the initial position with the final position? So initially it was here, then as a result it moved, it reached here, then we will have, this is the theta. So the position of A is equal to theta times the radius. So you need to memorize this one. So as I mentioned, since there is a point here and we need to study the motion of the points, the point located on the disk is considered as acceleration, is considered as particle that move translation motion, and it need to have SA, velocity A, and acceleration A. SA is theta times r, this is the theta. The velocity of A will be omega times the radius, and the acceleration at the point A will be the alpha times the radius. So this is how these four are connected together. So you may ask, what is the position of A? And it is giving this question with the radius information. So the position of A is the radius times the theta. If we ask what is the velocity of A at this point, what is the velocity of A? The velocity of A will be the omega times the radius, omega times the radius. And what is the acceleration of A, this point? It will be alpha times the radius. So we'll have position for A, velocity of A, and we have actually two types of acceleration, as we mentioned before. The acceleration, it will have normal acceleration and will have tangent acceleration. So the tangent acceleration is alpha times r. So this alpha times r is the tangent acceleration. And we still have also the normal acceleration, which is equal, if you do remember, v squared divided by rho. What is v squared? V squared is omega times r, or square divided by the rho. So it will equal omega square r square divided. What is the rho? Rho is the radius. So this one will go with this one. So it will end up with omega square times r. So we will have this one. So we have one, we'll have this one, and this one, and this one. So you can get the position, which is theta times r. If we give you this information, these three information with the radius, so it will be so much easy to calculate the position of A, the velocity of A, and the acceleration. We have two acceleration, the angular acceleration and the normal acceleration. And if we ask you what is the magnitude and the value of the acceleration, it will be calculated by using this formula. So in this chapter, we have four types of questions that you can expect. He might give you two disks like this one. He might give you two disks, one big and one small, and they are actually connected at this point. And for example, this is disk B and this is disk C. The name, let's give 1 or 2 or B or C or whatever you can name it. So the disk B and the disk C are connected together at this point, and let's call it A, this point A. This one is rotating at this direction, so this one will be definitely rotate at this direction. Since there is a rotation, so this disk will have theta, omega, and alpha. Theta for P, omega for P, and alpha for P. Here, it's rotating, so it will have theta, omega, and alpha. Theta for the C, omega for the C, and alpha for the C. So how these two disks are connected together, or what is the equations that related these two together? This is the relation. Omega B RB is equal to omega C RC. Theta B RB is equal to theta C RC, and alpha B RB is equal to the alpha C RC. So you need also to memorize this one. If you have this type of question, then this is the formula or the equation that you can start. What does it mean? For example, in the question, he might give you the radius of this one and the radius of this one. And he will give you, for example, the omega of this one. He will ask you, what is the omega of C? So it will be so much easy to have this one. Omega of P is given, the radius of P is given, the radius of C is already given, so you'll be easy can calculate the omega of C. The same also for the theta RA, theta RC, or alpha P RP is equal to alpha C RC. So you need to know these questions and determine what is available, and based on this equation you can get to know what is the requirements. Another type of questions is, we have one disk here that is rotated on this fixed point, and we have another disk here rotated at this point. We have a radius here. Let's call this one A, and this is this B. So this is the radius of A, and this is the radius of B. And how, since we have two, everyone it should have theta, omega, and alpha. If this is A, it will be theta for A, omega for A, and alpha for A. The same here for B. Since we have this rotated, so we will have theta for P, alpha omega for P, and also alpha for B. And how actually these are connected? They're actually connected similar to this one. So we start using also this one, which is I write it here the same, but since the name is different, so you can name it 1 or 2 or A or B, or he can also name it in the questions. So the omega of A RA is equal omega of B RB. Theta A RA is equal to theta B RB. Alpha A RA is equal to alpha B RB. So in the question the same. If we give you this shape or this shape, you will use the same equations. So he might give you, for example, this information and the radius of this one, the radius of this one, and he will ask you what is the omega B. He's giving omega A, for example, 5, the radius is 0.5, and the radius here is 0.2, and what is the omega or the angular velocity of P, so you can apply this one. This one is available or giving, this one is giving, the radius of P is giving, so it will be so much easy to get alpha P. So this chapter is so much easy. The third type of questions here, that if you have two disks and they are actually connected at the same time. For example, like there is a big disk here, and in the middle we have another disk, and they are connected with one fixed point, and both of them are rotating together. So here we will have, if this is disk 1, this is where R1, and this will be R2. And what is the relationship between these two? The relationship is that this one we will have omega 1, theta 1, omega 1, alpha 1. And for the big one, 2, it will have theta 2, omega 2, and alpha 2. We will have radius for 1 and radius for 2. So how these are connected, what is the relationship? He says that omega of A is equal to omega of B. The angular velocity of A, of this one, the big one, it will be the same as the angular velocity at this small one. So it is a double wheel. We call it a double wheel. So if we give you like the information of omega A, you need to know that you can use it at the same as omega B. You have the same value if you get this shape. The fourth type of questions, that if we have disk or rotating or wheel or gearbox or whatever it is, and it's rotating on a fixed point, the same as the before, and they are actually connected with a wire, connected with a box or whatever type of body here. So it will be something similar to this one. So we have a wheel and it's connected with a wire with a box here, and the wheel is rotating on this fixed point. It means it has theta, omega, and alpha. So what you need to know, as we mentioned before, if we have, for example, this one, and at any point we have theta, omega, and alpha for this disk that is rotated here, and at any point of point, let's say point P, so the velocity or the position of B is equal theta times the r, and the velocity of P will be the omega times r, and the acceleration of P will be the alpha times the radius. So if it's connected to this wire, he might ask you what is the velocity of this box, what is the velocity, what is the position, or what is the velocity, or what is the acceleration of this box here. What if this one is rotating, this one will go up. So we'll ask what is the position at a certain time, or what is the velocity and what is the acceleration. What you need to know that this is actually similar, that if you are getting the velocity and the acceleration and the position at the point that is linked with this wire. So imagine that you don't have all of this one and you want to get these points. And we have already discussed how to get the position, velocity, and acceleration at any point that is located on the wheel or on the disk. So it will be the position, as you remember, at any point, it will be theta times the radius, the velocity will be omega times the radius, and the acceleration will be alpha times the radius. So at this point, we will have get to this one, and this one will be the same as the velocity and acceleration of this particle. So you need to memorize also or consider that the position, velocity, and acceleration of this one, it will be the same as if you want to get the position, velocity, and acceleration at this point connected with this wheel. So this is all type of questions that you may expect. The first one, that he might give you two he might give you these two disks that are connected together at this point, so you need to apply this equation. Or two disks connected with the wires, it will be the same as this one. Or he gives you two disks are connected together with the same fixed point here. So you need to know, if you have this type of question, two disks with two radius connected at the same time, so you need to know that the omega of the first one is the same as the omega of the second one. If you have this type of question and he asks you what is the position, velocity, acceleration of this one, it's the same as if you want to give the position, velocity, and acceleration at this point that's connected to this one, and the position of any point will be the theta times the radius, and the velocity at any point here, it will be the omega times the radius, and the acceleration of any point here, it will be the alpha times the radius. And he might also give you the theta information, omega information, and alpha information, and by default he will give you the radius of this one, so it will be so much easy to calculate this information. So starting with the first question here, question 16.1 from the fundamental equations. The angular velocity of the disk is determined by omega, and he says that omega is a function of time, 5t squared plus 2, where t in a second. Determine the magnitude of the velocity and angular and the acceleration of the point A at the disk at t equal 5. So if we have this point, at point A, he asks of what is the velocity at A and what is the acceleration of A. We have two types actually of acceleration, the normal and the tangents. So if you want to get the velocity of any point here located on this one, it will be velocity, it will be omega times the radius, right? So omega is given us as a function of time, so we can get the omega here, 5t squared plus 2, this is a function of time, and he asks us at this time, so we just plug in when the time is 0.5, we plug it here, then we can get the omega value. So the velocity, it will be omega is 3.25, we calculate it here, times the radius. What is the radius? 0.8 times 0.8 meter. It will end up with the 26 meter per second. And you need to know that you need to always convert to a meter. Here is a meter, but in another question, you start to give it you in millimeter. You need to convert it to a meter. The other requirement is the accelerations. And the acceleration is the tangent acceleration of this point will be equal to the alpha times the radius. And actually we don't have alpha, but we do remember that we can get, this is he give us omega is a function of time, right? and we can get the theta and we can get the alpha. We're moving like this one, we differentiate. So we have this one as a function of time, so we can calculate the alpha. So alpha will be the derivative of omega with respect to time. So it will be the derivative of this equation, which is omega at a specific time. So we can come up with the alpha. So it will be 5 times radius is 0.8. So it will end up with 4 meters per second. The second type of acceleration is the normal acceleration, which is rho, or we already calculated omega squared times r. Omega is already calculated, 32 point here. This is the omega of the questions, and the radius, we already have the radius, so it will be so much easy to get the acceleration, normal acceleration. And he asked for the magnitude, so it will be the magnitude of A is equal A tangent square plus A normal square here, and we'll end up with this value. So this is the simplest question that you can see related to this equations, or related to this chapter. Another example here, or question 1612, he says that the power of bus engine is transmitted using a belt and pulley arrangement as shown in this figure. If the engines turn a pulley A, this one disc, you start to call it pulley or disc or whatever you can call it, is giving omega A is a function of time. So we have 1, 2, 3, and 4. We have 4 pulleys or 4 discs. This is A, disk A, and this is the big one is B, the small one is D, and this one is C. So we have 1, 2, 3, and 4, and this is how the way they are actually connected. So what is giving in the questions is giving omega A is a function of time, which is 20 time t plus 40. This is omega of A. So for each disk, it should have theta for A, omega for A, alpha for A. For this D or P, we will have theta for P, omega P, and the same as for the alpha, the same for the D, and also the same here for the pulley C. We need to have theta C, omega C, and alpha C. So what is asking, what in the second, determine the angular velocity, it means omega, angular velocity of the generator of pulley P and pulley C. So pulley P, he need omega P, what is omega P and what is omega C. So this one is just linked with the omega. He doesn't give any information about theta or alpha, so it will be so much easy. And we have seen that this type of connection, if you do remember here, it will be similar to these type of questions, that if we have two pulley or two discs are linked with a wire, then we start using these equations. Omega, they are actually linked with the radius. So we have, this is 1 and 2, so it will be omega for 1 R1 is the same as omega 2 R2, or B and B or C. So in this question, he is giving us omega, A, which is a function of time. So in order to get this one, omega b is the only available information is omega A, which is a function of time. And omega b A is not actually directly connected to P, it's connected with the D, and D is actually part of this one. So we need actually to calculate length between A and D first in order to get omega D, and omega D will be the same as omega B, as we see here, as we see at this type of shape. If we have two discs at the same body and they are rotating at the here, the omega of that one will be the same as the omega of the bigger one. So we have omega A as a function of time. We calculate first omega A, and he needed at time equal 3 seconds. So omega A is 20 times t plus 40 at t equal 3 seconds. We plug the 3 here and we calculate it. We can get this is omega A. Then we start to link this pulley with the small one, and all of them is giving the radius is giving. The radius of this one is 75 millimeter. The radius of D is 25 millimeter. The radius of P is 100 millimeter, and here the radius of C is 50. So it's so much easy. You need first, in order to get the omega of this one big, we need to get from here to get this one, and this one will be the same as this one. Then from here we can get this one linked with the radius. So the first thing that we calculated omega A, which is 100. Now we start to link this pulley A with the pulley D. So how it that links? Omega A RA is equal omega D RD. Omega A is already calculated 100. RA is giving, this is millimeter, we need to convert it to a meter, which is 0.075 equal omega D is not giving, the radius of D is giving. So among this one we can calculate omega D, and omega D here is the same as omega B. So omega D is equal to omega B, which is the same as 30. Now we start to link this one B with C with the radius omega B, that one R, the radius of B is equal to the omega C RC. Omega B is already calculated 300, the radius is giving, omega C is required, RC or the radius of C is already giving here 0.05 because we converted to a meter. So among this one we only missing this, so we can calculate omega C. So this is the easiest question. This is type of question that we can expect during the exam or the homework.